and welcome to the 13th lecture in this series, and we were discussing some examples of smooth maps between manifolds, and I was dealing with the case of product manifolds towards the end of last lecture. So let me resume that. So I have a product manifold M1 cross M2, and let's fix a point B in M2. Corresponding to that B, I have a map of M1 into M1 cross M2. Namely, I just take X and put it the Y coordinate, the second coordinate to be B. So schematically, what are we doing? Well, let's say this is M1, this is M2. So if I take a point B for every B in M2, I have a copy of M1. So I have a copy of M1 sitting in M1 cross M2. So this is the second coordinate is fixed to be B, and the first coordinate varies over, this X varies over all points of M1. So the picture sort of illustrates why this is called a slice. So all these are slices, horizontal slices. Similarly, I have vertical slices as well. Similarly, fix A in M1 and define IA of Y to be A comma Y. This IA is a map from M2 to M1 cross M2. So it puts sort of just puts M2 inside this product. It doesn't really do anything to the point except that it puts it at sort of, you can imagine it as in the case of the horizontal slice, it puts M1 at different heights. And in the case of this vertical slice, it puts M2 in different horizontal locations. These are all of course the picture should not exceed. So these are the horizontal slices, and vertical slices will be like this. So all you're doing is just putting M2 at different sort of locations. Now these slice maps are smooth. So IB is smooth at all points of M1, IA is smooth at all points of M2. And in fact, so here again one can just take some coordinate chart. So here one has to start with a coordinate chart around a point in M1. Just use the same coordinate chart as a part of a product coordinate chart in M1 cross M2. It doesn't matter what coordinate chart you use for this B in M2. But for M1, just use the same one. And one will, in local coordinates, this will be a slice map between, so in U1 cross V1. So this will be in Euclidean spaces now. So this U1 and U1 cross V1. So it will be of the form again X comma. So this is in the local coordinates. This will be a slice map between. So in the first case meaning this maps of the type IB, where the second coordinate is fixed, it will be of this form. So B1. And we know that between domains in Euclidean space, such a map is trivially smooth. So the corresponding map between manifolds is smooth as well. Now let's look at something more specific. Let's look at a rotation map on S1. Let theta belong to 0 to 2 pi and let a theta be cos theta sin theta minus sin theta cos theta. Now if P belongs to S1, then S1 of course regarded as a subset of R2. So then a theta of P also belongs to S1. Well, this is a rotation matrix, so if P belongs to S1 just means that norm P is 1. Since it's a rotation matrix, a theta P also has norm equal to 1. So a theta is a map from S1 to, and this a theta rotation map is smooth. Of course, one can use either our we have constructed two coordinate systems on any sphere. One is the projection, where the charts are just projection maps, and the other one is stereographic projection. One can use either of them to check that this is smooth. But a more efficient way of doing things would be later on. We'll prove that later that if you have any smooth function from Rn plus 1 to Rn plus 1 is smooth, and f takes the n-dimensional sphere back to itself, then if we regard f as a map from the sphere back to itself, forgetting Euclidean space, this map is smooth. So the map if we know that the map between the bigger Euclidean space is smooth, and of course if it takes the sphere back to itself, otherwise this doesn't even make sense. So we need the sphere to go back to itself. Then f as a map from Sn to Sn is also smooth. And in fact this is just a very special, this will be a very special case of map between submanifolds and so on. So, but the thing is that it's rather than work with some coordinate charts on S1 and trying to prove that this map is smooth, it will be, we'll give a much neater proof that this, for instance, that this rotation is smooth. All right. So now that we have notion of smooth maps, let's we want to talk about another very important, in fact the fundamental notion sort of associated to a smooth manifold is that of a tangent vectors and tangent spaces. So the moment you have one has a smooth manifold, by its very definition, one has at each point to the smooth manifold, we will define a finite dimensional vector space called the tangent space. This notion of tangent space is going to play pretty much whenever one deals with smooth manifolds. This will automatically make an appearance. So, so let's now the way a tangent vector is defined, there are several possible ways of defining this. But whatever way one chooses, whatever sort of definition one works with, a certain amount of abstraction is necessary, because the whole point is that when we say something is a manifold, the definition doesn't assume that whatever we have is a subset of Euclidean space. Locally, of course, we know that it's homomorphic to Euclidean space, but overall, the whole set need not be a subset of any Euclidean space. So, one cannot use the Euclidean space in any essential way while talking about tangent vectors. So some amount of abstraction is inevitable. So to motivate this, the definition of a tangent vector, let's in fact start with the simplest manifold, namely Euclidean space itself. So let's start with, we already know how the case of Rn as a manifold. So we have an idea of how to talk about tangent vectors and tangent vector at a point in tangent vector to Rn at a point. So given P in Rn, V in Rn. In fact, let me just modify this slightly. It's a bit confusing if one works directly with Rn. A clearer thing is the case of an open subset U contained in Rn. So I would like to what I'm trying to do here is, my manifold is the open subset U in Rn, and we already know that the given, so this is U and I have a point P. For instance, if U is in R2, let's take this simple case. Well, tangent vector at any point, normally one thinks of an arrow based at P and pointing in some direction. This of course doesn't make sense, but in effect what one is saying is that one is looking at all possible directions in which one can move and moving yet remain within the manifold. If we have an open set, of course, whatever direction you move in for short distance, U will end up inside U. So from naively, every possible direction is a tangent vector. So any V in R2 would be a tangent vector at P. So at the end of the day, the tangent space, a tangent vector would be just a point in R2, this V. However, this won't do when we talk about manifolds. So let's look at it from a different point of view. So let's start with P. Again, I'll just take U. Let's take a point P and a vector V in Rn. As we just discussed, any point in any vector in Rn can be sort of intuitively regarded as a tangent vector at P. Any element of Rn can be regarded as a tangent vector at P. But I want to get hold of this V in a more abstract way. So instead of this V as a point in Rn, let me define a map. So first let C infinity U denote the set of C infinity functions from U to R, real valued C infinity functions on U. Here I said that set of C infinity functions. Of course, since the target is R, this is actually a vector space. I can add two such functions, multiply them by a scalar and so on. Is a vector space over R. I want to define, now I've taken a point P and a V in Rn. Corresponding to this, I'm going to define a map. Define a map from TV from C infinity U to R So to every C infinity function, I want to get a real number given this point P and this vector V. Well, we know what to do. We can just take the directional derivative of the function at the point P in the direction V. So let's of F is just what I have denoted earlier by V of F, which is d by dt f of P plus TV at t equals 0. So I just look at the straight line starting at P in the direction V. For small t, when this line will be contained in the open set U, and small t is all that matters for taking the derivative. So this will be contained in set U, and then I have this function f. So I restrict f to this straight line and then take the usual one variable derivative. So I get I have this thing. So in short, it's just the directional derivative. But our viewpoint is that this we have fixed V, and of course we have fixed the point P, and for every V we get a map. Note that one, TV is linear, i.e. TV of C1 F1 plus C2 F2 is TV C1 F1. For all C1, C2 real numbers and F1, F2 C infinity functions on U. So this is actually this is not so evident if from this formula that I wrote down here, but we know that this is actually given by, this is also equal to DFP of V. So recall that F was a map to R. So I have the derivative as a linear map from this to this. So I can act on this. And the derivative as a linear map has components given by partial derivatives. So this is also equal to del F by del X1 at P, V1, etc. where V equals V1, V2, Vn. So this, there are several ways of writing the directional derivative. The definition is this, d by dt of this, but that's the same thing as dfp acting on V, which is also the same thing as this. If we use the second one, dfp of, right, no, actually, yeah, for this one, it's one can use any of these. The linearity with respect to functions, even if you use this d by dt of f of p plus tv, it is clear enough. Or I can use this here, or I can use any of these three things will show this linearity with respect to functions. Later on, I'll be needing linearity with respect to v, then one will have to use a different one. At this stage, any of these three things will do. So TV is linear. The second crucial thing is that TV satisfies the Leibniz rule. So what does this mean? Well, this notice that the C infinity U is not just a vector space, but also there's a multiplicative structure involved on this. So in other words, if I have two C infinity functions, I can multiply them and get another C infinity function. So let's do that. So I have two functions f and g, and if I take TV of fg, so I'll just get d f of p tvg plus g of p tvf. So in other words, we have a product rule for derivatives. That's all we are saying. And this again follows from, for instance, any of these three things. Especially the first one makes it quite clear. This definition of TV, instead of f, I'll be working with f times g. And then one can use the usual product rule and get this. So what we have is, so what we have done is, for so a brief summary is, for each V in Rn, we have a map TV from C infinity U to R. All this is happening with the point P fixed. Notice that this Leibniz rule property that I have here, the point P plays a crucial role. This P occurs here and here. So that is always in the background. So we have a map TV from this to this, which is linear and satisfies Leibniz rule. So we say that such a map is called a derivation on C infinity U. So a linear map satisfying the Leibniz rule is called a derivation. Well, actually a derivation is something more general than this and defined on more general objects than C infinity U. In this context, as it turns out, giving it a new name turns out to be unnecessary, because it turns out that a derivation has to be something very specific. It's more or less like it is, in fact, our main result is that the following, that it is going to be a directional derivative. So theorem let T from C infinity R, C infinity U, C infinity U to R be linear and satisfy the Leibniz rule, i.e. TFG plus F of P TG plus G of P TF. Then T equals TV for some V in Rn. So in other words, if you start with an abstract, with any map from C infinity U to R, which is linear and which satisfies the Leibniz rule, notice that this Leibniz rule, for this Leibniz rule to make sense, one doesn't have to really talk about derivatives. All one is doing is considering the action of T on a product function, and we are saying that T of Fg has this very specific form. The point is, this second condition, this Leibniz rule condition, is so strong that this forces any such map to be necessarily a directional derivative with respect to some vector V in Rn. And so I should mention that note, C infinity U is not a finite dimensional vector space. This is obvious, since you have an infinite set of linearly independent vectors. So since 1x, if I take, is linearly independent for any k, any k in z plus natural numbers. So in other words, there is no bound on the size of on how many linearly independent vectors we can have. So we can have arbitrarily large set of linearly independent vectors. This is not a finite dimensional vector space. And if therefore the set of linear maps from C infinity U to R associated to every vector space, we have the dual space, i.e. the dual space is also not finite dimensional. It's easy to see that if a vector space is not finite dimensional, the dual space is also not finite dimensional. So if we just had in this theorem, there are two conditions on T. One is it's linear and then the Leibniz rule. If we just had linear, then the set of such maps would be a very large space in the sense that it would be an infinite dimensional vector space. However, the moment you impose linearity plus Leibniz rule, the theorem tells us that the set of such maps is severely restricted. In fact, each map corresponds to, so here actually I should add that for some unique V. So for every such map there is exactly one vector, a corresponding vector in Rn. So in other words, set of such maps is in bijective correspondence with Rn, which is a finite dimensional vector space. So just linearity would give an infinite dimensional vector space, while this linearity plus Leibniz rule gives us Rn. So let's stop here. Next time I'll prove this theorem and then use this to talk about defined tangent vectors on manifolds and tangent spaces, and then we'll proceed from there. Thank you.